Thank you, Kiran. Thank you, everybody, for being here today. And I would like also to thank the organizing committee for this opportunity to present this work. So since the workshop is about the future, I'm going to talk today about a new architecture we are working on in ETS Montreal. This architecture is called FlexNGIA, and it's basically a fully flexible architecture for the next generation tactile internet. So I'm going to start my talk first by having a glance into the future. What kind of applications we are expecting to see in the near future? What are the limitations of today's internet? What are the main features of the proposed architecture? And through some use cases, I'm going to show you how this architecture can support future applications. So I'm going to only present the main feature of the architectures, but you can find more details in this paper, which is already available online. So let's go first to the future, okay? So as you can see here, we have like some applications that we already have, but they are not very common yet, okay? We don't really commonly see telepresence, like remotely controlling robots, virtual reality, augmented reality, holoportation, like porting holograms from one location to another, haptics, like communicating the sense of touch, right? So all those nice applications are expected to be the main applications of the future, okay? Something is wrong here, something is loading. So let me take a few seconds and ask you to do something. So since we're talking about the future, I'm gonna rely on your imagination. And I would like you to imagine that we are now in a virtual environment. So you are sitting at your place, and all what you see here are just holograms, maybe robots that are remotely controlled, right? So take a few seconds, look around, and enjoy like this virtual environment, enjoy those virtual people, right? So so basically here, this reminds you of the famous movie, The Matrix, right? So, and let me welcome you to The Matrix, and this is basically the sentence that have been told to the main character of the movie when they told him that he's not living in the real world, he's living in the virtual environment, right? So let's see, so we're here in the virtual environment, and if you would like to implement this, so what are the requirements and the characteristics of this application, okay? And let's take this use case that I just described as a typical use case. So as you can see, the main characteristic of this application is that it's like an octopus-like application. So we have a huge number of flows coming from different sources to different destinations. We're here more than 100 person in this room, so you can imagine how many flows we are exchanging between us. Okay, so this is a huge. So another characteristic is that the requirements are changing over time. So now I'm in the floor, so most likely I'm the most important person here, and the flow that coming from my location is the most important flow, okay? So over time, after 1 hour maybe, there will be another speaker, and the requirements will change over time, okay? So if you would like to implement this, for sure we will need a high processing power, right? So we need to process at real time all the traffic coming from those sources, right? Compiling those holograms, compressing data, and so on. So we need real-time processing. We need high bandwidth, and I give you the example of a virtual reality example with 16K to 240 frames per second, and this is basically the requirement to have a really immersive virtual environment, and this would require at least 31 gigabit per second just for this virtual environment. Not talking about each hologram. Okay, so we need a huge amount of bandwidth. So even if we have a lot of bandwidth today, this is not sufficient, right? We need also ultra low latency. It can go from 1 millisecond to 20 milliseconds, depending on the interactivity of the application, right? Just to tell you that to communicate the sense of touch, we need at least a 1 millisecond of latency. So we have also another challenge, which is the multi-flow synchronization. So I'm a hologram, I'm trying to shake hands with another hologram. So you can imagine the synchronization needed to make this thing happen, right? So far, like we still have trouble synchronizing the sound with the video, right? But imagine like in this more complicated scenario. So we need also high availability of the network. So for applications like telesurgery, for example, so availability is key, okay? So what are the limitations of today's internet? Why internet today is not able to fulfill such requirements? I'm going to talk first about the internet infrastructure, the services offered by internet today, and I'm going to look at the network stack, the problems with different protocols today. So today's internet is a network of networks, okay? So the main problem of internet today is that it delivers only a best effort service. So basically the main output of each of this network, the main role of each network is to deliver the packet. So get the packet, I will deliver it, and that's it, okay? So we don't have a full control over all the infrastructure because we have different ISPs, okay? So we don't really control the quality of service, and at the end of the day, we were not controlling the performance of the internet today. If we look now at the protocol stack of the internet, so the application, more or less, we have control over it, right? We are implementing the application. So we'll jump into the transport layer protocols. So there are many modern protocols like HTTP, quick, but I'm going to focus first on TCP. So TCP has a lot of problems. First of all, it's a one-size-fits-all service offering. So basically, it will offer you reliability, data transmission, congestion and flow control, and you have to take it all or leave it all. Just go with TCP and get all those features or not, okay, with UDP. So this is not always interesting because sometimes we don't need reliability. Sometimes we need reliability only for some of the packets, right? So there are different offerings that cannot be fulfilled by TCP. Another problem with TCP is that it does blind congestion control. So TCP today is not able to be sure that a packet has been lost, right? Tries to guess, okay, I have a timeout, I have duplicate acknowledgement, maybe a packet is lost, right? So this will generate a lot of retransmissions, and we are, at the end of the day, we are not really sure whether a packet has been lost or not. Another problem with transport layers today is that they consider only two endpoints, okay? So basically you have the two endpoints that try to manage, and one direct implication of this is that we have high retransmission delays. Okay, so if we have a packet that's lost, so it would require 3 times the end-to-end delay to retransmit it. So 3 times the end-to-end delay, this is a huge. Okay, so we can imagine another case where the network itself detects the packet loss and retransmit it. So we can reduce those delays. Okay, so another problem with today's transport protocols is that the transport and the network layers are not aware of which flows belong to which application. So all of us are exchanging data here. We have huge amounts of flows, but the network itself doesn't know that all these flows belong to the same application, and it needs to take into account this feature to decide which flows to prioritize, which packet to drop, and so on. Okay, so the network today knows only that I have a communication between those 2 endpoints, but not multiple endpoints at the same time. So if we look at the network layer protocols, so the main problem with the routing today is that they are not aware of the applications. So they are not aware of the composition of the application, as I just explained, and it's not aware of the performance requirements of each of these flows. So I give the example of our application here. So if I'm talking here in the floor, so my traffic coming from me should have the highest priority. Okay, and the network should take into consideration that. Okay, so basically today's network, they will drop packet blindly without taking into consideration the flows and the importance of the flows that are coming from different sources. So in today's networks, there is no collaboration with the transport layer. So there's like the ECN, ECN provides a little bit collaboration between the network and the transport, right? But this is not enough. With ECN, for example, we cannot locate exactly where the congestion lies, for example, okay? So the network today does not help with other transport services. One of the main transport services is reliability. And what if the network itself retransmit a packet because this packet is important, right? We don't have to wait for the endpoint, for the source to retransmit it. So we will save a lot of time. So if we look also at the network stack headers, the different headers of the packets, so usually we don't have a lot of information about the objects, the sensors, the flows, the membership of the flows of each application, the application requirements, and so on. So it's still not flexible enough, and it's not easy today to incorporate metadata or commands. Okay, metadata to provide more information about the application, the status of the application, and commands that could be executed throughout the way, right? So starting from there, we started to think about a new architecture, and I'm gonna go through different points to explain this architecture. So we're going to look at how the internet will look like in the future, what kind of service it will offer, the business model, what kind of management framework we need to manage the network, the network style, the functions, and the stack headers. So let's start with the first point, how a network will look like in the future. So the main feature of the future networks is computing resources. Computing resources are everywhere, as you can just see here. Okay, so we have here point of presence, but the point of presence have also a huge amount of computing resources. Okay, so these computing resources will be made out of from commodity servers, but also from FPGA, GPU, NPU, and so on and so forth. And the main advantage of having this is that we will be able to do in-network computing. So the network itself will be able to process data and do all kinds of operations inside the network. So this will reduce significantly steering delay. What I mean by steering delay is that today, most of the time, we send the traffic to somewhere in a data center to be processed before sending it to the final destination. Okay, so this will add additional delays just to send the traffic to be processed and so on. So if the network itself is able to do the processing, okay, we will process the traffic throughout the way, like for example, through the shortest path. Okay, and of course, this will offer us the promised full programmability. You can provision any function anywhere in the network. Okay, so today we are doing this using virtual machines, containers, but there are other technologies like P4s and so on that can be that are used today. So regarding the internet, how does the future internet look like? It will be always a network of networks, but what will be new is that each network will offer like more than delivery. It will offer, for example, what I call here service function chains. Okay, so a set of functions that will be offered by each network. So these functions can be more advanced. It's not about only delivery. Like the network can process the traffic, can compress data, and so on. Okay, and of course we need to for each service we need to guarantee like stringent performance requirements in terms of delay and so on. So here I'm providing an example of a service function chain. You can see here that we have so there's different functions. Okay, so I have traffic coming from different sources. So we have sensors here. Okay, so the traffic comes from the sources, from the sensors, and go through the different network functions to reach multiple destinations. Okay, so here for each network function, we need to define the type of the function, the software that should be run to offer this function, the input and output packet format. So we are not restricted to a particular packet format. So when you define your function, you say, okay, this is what I expect as a format, and this is my output format, the expected processing delay, the buffer size, and so on. Okay, so if we look at the service as a whole, we need to define some performance requirements like the throughput for the whole service, the packet loss, the end-to-end delay, and so on. Okay, so here we need to define. So when you design your application, you design a service function chain, and you provide your requirements. Okay, so what we expect is that in the future, we will adopt a business model that's really similar to the cloud computing business model. So basically, we will have network operators that will own the physical infrastructure, the computing resources, the network, and so on. And it's their role to offer service function chains as a service. So you're a customer, you will define like your own, what you need as a service function chain. Okay, so the service function chain composition, the requirements in terms of bandwidth and end-to-end delay, reliability, and so on. requirements for each network functions, processing power, packet format, packet drop criteria, and so on. Okay, and you'll ask the network operator to provision this for you. So I'm providing here some example of network operator that can offer such a service. Of course, like the popular network operators like AT&T, Bell Canada, or can offer this if they have computing resources. But we can easily see that web-scale companies like Google, Facebook, and Amazon, they already have like such infrastructures. And I'm giving here the example of the Google Cloud Platform, which is a worldwide global infrastructure that's software defined. So everything is controlled using software. And the biggest advantage of Google today is that it has a full control over infrastructure that's spanning the whole world. You can see here in those nice figures, what's in red here, the red bullets, these are the data centers of Google with huge amounts of resources. The blue bullets are 100 points of presence, and they have computing resources. And Google has today more than 1,000 edge nodes with computing resources. So basically, if Google decides to provide like a service function chain as a service, it's easy to provision that. So in order to manage those service function chains, of course, we need to have a resource management framework, right? So the main role of the resource management framework is to allocate the resources, like set up the network, the service function chain, and so on. So let me start before getting into the details of the framework. Let me start with an example of a resource allocation. So here I'm providing an example of a service function chain. So basically, I'm the application developer. So I develop. Okay, I need the service function chain with those functions, and if I provide the sources and destinations of my traffic. So the first step is to do some kind of translation. And basically, the translation will, during the translation step, we will decide how many instances of network function 1 we will need. For example, here, for this function, we will need 3 instances, okay, 3 virtual machines. Okay, this one, we will need 2, third one, we will need 3. Okay, so of course there are different criteria to decide how many instances do we need for each function. And the next step is to do the mapping. So basically mapping is placing those instances inside the network. Okay, so many criteria should be used to place those instances. Okay, so this is basically how the resource management or resource allocation process works. And if I go quickly through the resource management framework, so basically we will have multiple service function chains. Okay, for each service function chain, we will have an application control module. So this module will monitor the service function chain and will decide, for example, of the number of instances. Will check whether the requirements are met or not, and so on. Okay, if it decides, like for example, it needs more instances, for example, it will communicate with the resource allocation module here. That will provision the required resources. Okay, so of course here we have a signaling module. So the signaling module is used mainly to create a service function chain or to request a service function chain and send the requirements to the resource allocator. So let's move on now to the network protocol stack and functions. So basically in FlexNGIA, we assume that in the service function chain, we will have always the basic network functions, like packet forwarding is a basic function, right? But we assume also that we will have more advanced network functions that could operate at any layer of the network. So they are only limited by our imagination. We can have network functions that can operate at the application level, at the transport or network level. We have others like that operate at the different levels of the network stack. So we can imagine a lot of functions: packet grouping, caching, packet caching and retransmission, data processing at different levels, even at the application level, application-aware multiplexing, and so on. Okay. So of course here the functions will probably break the end-to-end principle. Okay. So here I was talking about packet caching and retransmission. So basically we are processing, we are breaking the end-to-end principle of TCP. So there is no TCP anymore. Okay, so we need probably to extend also SDN Okay, so today's SDN focus mainly on on configuring the forwarding rules, for example, through OpenFlow. But if we imagine like network functions that can operate at different levels, we need APIs to control those functions, of course. So this is what I called here SDN++, and the idea is to go beyond configuring forwarding rules to configuring more network functions, more types of network functions. So as you can see here, we have two particular network functions that we are introducing in FlexNGIA, and mainly the application assistant and the transport assistant. And these are quite particular case of network functions. I'm going to go quickly through the role of each of these functions. So for the application assistant, the idea is to have an application assistant at each endpoint. So basically, we have sensors. We have a lot of data coming on. For example, we have cameras taking like trying to capture the holograms. Okay, so the application assistant will try to analyze all the data coming from the sensors and decide which data, for example, is important. The application assistant will add, for example, metadata about the context of the application and so on. Okay, so we have, as you can notice here, we have an application assistant at each of the endpoints, and this is basically the first network function that the traffic will hit. Okay, and you can see it as a translator. So it will receive traffic from the sensors and will translate all what's coming into a requirement to be sent through the chain. Okay, so this is first particular network function that we define. We also advocate for another function that's interesting, and basically this function will do the job of the transport layer, and this is cross, so here in FlexNGIA, we would like to merge the transport and the network layer. Okay, you said like the TCP is doing things blind, is detecting congestion blindly and so on. So we're trying to avoid all this and to have a cross-layer transport. And this cross-layer transport is implemented in a particular network function inside the network. So we can have multiple instances of the transport assistant. And I'm not gonna dwell into the details, but the main feature, I can give you some interesting feature. For example, the transport assistant will do congestion control from inside the network. Okay, so if you have a portion of the path that's suffering from congestion, the transport assistant can cache packets, retransmit them, okay, or can adjust the rate, like do congestion control based on this particular portion of the traffic. So I will show you another, in the use cases, we will talk more about this. So in terms of packet header, so in FlexNGIA, we advocate to have just two types of packets. So the first type of packets that we have signaling packets. So these packets are used to request a service function chain and instantiate a service function chain. And we have also the data packets. So their main role is to carry data. So our idea is to have only a layer 2 header. So FlexNGIA only fixes the layer 2 header. We will have something similar to VLANs, but that can span different domains. So we'll have like an application ID. Okay, and wherever you go, you keep this application ID, and I mean wherever you go through the domains, right? So you can be routed through this this application ID. You can see that like a big VLAN that spans multiple domains. Okay, so on top of that, we will have upper layers. So with FlexNGIA, the upper layers are fully flexible. So basically, when you define your service function chain, you specify exactly what kind of header each network function is expecting and what kind of header it will generate. Okay, so we have a fully flexible packet header. So now I'm gonna finish my talk with some use cases. Okay, some use case scenarios. So here I'm going to provide like some details of two use cases, but you can find more in the paper. So one example of use case is network assisted data transport. So the goal is to minimize retransmission delays. So we said like doing retransmission from the endpoints will incur huge amount of time. And here the idea is to minimize the delay and improve the congestion control. So what an example of solution is to have a service chain with a transport assistant function. Okay, so we have here your chain, the source, destination of the traffic, and you have the transport assistant. Okay, so once this chain is translated and mapped into the network, so we will have like two instances of the transport assistant. So you can see here from 0, so the traffic will go to destination 13, and we have like 2 transport assistant. So this assistant here will cache packets, for example, and retransmit them. So we don't need to retransmit from 0. So we have another one here. So you can ask me why 2 transport assistants, right? So this is one of the challenges that we need to think about, right? For example, we can add transport assistant wherever we have a portion of the path that has congestion, so we need to have those transport assistants, okay? So basically, transport assistant will cache retransmit packets, will detect the packet loss, can do congestion control, adjust the rate, drop packets, do some compression if needed, and so on. So another example is an example of a mixed virtual reality and holograms. So here we have, in the example, we have like H1, H2, and VR. So this is hologram 1 from the source, hologram 2, and the virtual reality environment. And we need to teleport all those holograms and virtual reality environment into 3 destinations at the same time. Okay. So here in this example, we have like 3 types of network functions. We have an encoder to encode the incoming traffic, like the data and so on. The transport assistant to improve reliability, and the video cropper. So the idea of a video cropper is that we don't need to send all the data to everybody, right? So at some point, maybe we will send all the environment, for example, to the 3 destinations, but inside the network, for example, Professor KK is looking at me, I can crop all the data and just send the traffic of me, right? Of my hologram, right? Depending on the context of the application, okay? So, so you can see the different steps. So we translate this. So here we decided that we will have 3 instances of the encoder, 2 instances of the transport assistant, and 2 of the video cropper, okay? And then we have the mapping process, so basically the slicing, okay? So we need to map this. So why 2, 3, and so on? So there are many criteria to take into consideration, okay? So here is just an example, okay? So just to conclude, so basically the main features of this new architecture that we have computing resources everywhere, so we rely on that, okay? And I think the keynote today, Professor KK work, like they focus on how to leverage in network computing, how to improve like the performance of softwarized functions. Okay, so basically the main advantage is that we can have any function anywhere in the network. The business model, it's quite similar to the cloud computing model today. It's like we are expanding the cloud into the network. Okay, so the idea is to offer service function chains with multiple sources, multiple destinations, and to have stringent performance requirements, because we have, like, we are doing mapping first, so we need to take into consideration all the requirements. The cross-layer design, so here we are advocating to merge the transport and the network layers. So we are breaking the end-to-end paradigm. So we are changing things, changing the data throughout the communication. We are adopting advanced transport functions. So we assume that we will have like better congestion control. We can better respect the performance and reliability guarantees. We have application-aware network management, so we can have advanced functions tailored to the application. We are not restricted to what's offered today. Okay, and finally we have fully flexible headers. So you tailor your headers depending on your requirements. Okay. So if you'd like to read more about this project, so you have like, please, you can check my webpage or read this first paper that we already published. So the project is, I mean, we are doing this in ETS. So many people ask me, oh, what's about ETS? So ETS is the School of High Technology. It's the second largest engineering school in Canada. Okay, so you're very welcome to visit me, and if you drop by Montreal. Thank you very much.
Thank you, Professor Fadhan. Do we have any questions?
Very interesting piece of work. So are you guys actually building this proposed architecture?
Yes. So what we are trying to do, so there are a lot of challenges, right? So we are taking things like one piece by one piece. I think your work is focusing on many challenges related to this work. Okay. So currently we are focusing on the. So I put here some some of the challenges. So currently we're focusing on the slicing, okay, the mapping thing. So we already have like some code running, and probably it will be open source soon. And we are looking also on for working also on a distributed cross-layer transport protocol. So the transport assistant, the retransmission, and so on.
How large is the team?
Currently we have 1 postdoc, 4 PhD, and 2 masters. Probably soon we will be able to double the team.
So it's a very ambitious kind of project also.
Yes. Thank you.
Any other questions here? So Professor, I have one question. It's mostly curiosity. You talked about flexible headers and only 2 kinds of signaling formats. L2 header was present. We had service function chains. I did not see anything resembling network layer or IP addressing for that matter in order to handle the routing or the forwarding decisions. What's your plan in this project?
So the idea here is to have like, so it's like to have a VLANs, okay? VLANs, but that can span different domains, okay? So we're doing this somehow like even today because we're able to identify the flows, right, through the headers. If you look at the TCP header plus IP header, we are identifying the flows. So we can easily identify an application and use that, okay, to do the routing throughout the network, okay, throughout multiple networks, multiple domains. So maybe it's not realistic, it's not to be applicable today, right? So we cannot do this, but the idea is to do forwarding just like a VLAN, right? Just look at the 1 parameter and do the forwarding. If you would like to do more, you can go to the upper levels and take decisions based on the upper levels. But at least when you define your service function chain, you can do forwarding. The packet can go from the source to the destination using just the VLAN tag.
Okay, so it's more like layer 2 level addressing is used for forwarding.
Exactly. So the basic thing is layer 2, but your function, network function can go beyond layer 2 if you'd like to do more operation, right? But with layer 2, you are able to send the packet from one source to one destination. Okay.
Interesting. Thank you.
Yeah, thank you.
Any other questions here? If not, then we would like to thank you, Professor Fadin.
Okay,
and
thank you very
we'll
much.
see you at the panel time.
Thank you.